How we could tackle that problem? My first intuition was to let's create some kind of geospatial model, just using the x and y of the space, right? Like we have the latitude, and we can say we have the x and y. We create some kind of additive model, very smooth over the space, something like this. And we will maybe it won't be the final model, but we will have some kind of basic model, some kind of baseline from where to start. By the way, why I'm putting like I don't know if you realize, but here's a basketball court. It's because just before that, I was working on a project related to basketball, where I did that. I had 10,000 shots from the NBA from a season, with which shots which were made and which were failed, and I did exactly that. I had so much data, I could create this called generalized additive model. Then it's basically a model which is very smooth. So then you can plot it over the field, and you can say, my model is basically in the red areas, people make more shots. In yellow areas, people make less shots, and it looks very cool, and it's a good starting point, right? So when I came with this, so since my previous project was related to this, I came very biased. I came like, okay, let's do this. Let's take just the x and the y, right? Let's take for example, what's the x and the y here, the x and the y here. Let's estimate some model. Let's make it very smooth, and then we superpose that model over all the region, okay? The problem with that approach is that we didn't have enough support. This makes sense for that case of the basketball because I had 10,000 basketball shots all over the area, so I have support like in most areas. Okay, so I have, I don't know, 100 shots taken here, 20 here, 30 here, 500 here, and the model will more or less give reasonable estimates. What we have here is first we have very few points, very few support points. And most of them, they are in the same area. Like in this area of San Francisco is where more restaurants are. And so if I tried to actually do the idea, but the model looked awful. It wasn't like a good approach. Okay, it doesn't mean that we couldn't use the x and the y on the space, but it wasn't enough. Okay. So as most data scientists, I'm very biased to see every problem as a supervised learning problem. Not all of them, of course, but I also have that bias, right? Okay, if we want to predict, we want to do something, let's try to do some kind of supervised learning approach. Okay, that sounds reasonable, like a framework, but what features do we have? Okay, and actually it came that these people had a lot of data. Actually, the promise when I came to this project is like, we have a lot of data for you. You will love this problem. So I came to solve this problem as a big data problem, actually. That was the promise. I didn't know what I was going to see later. Actually, it was the opposite. So it is true that they did have a lot of big data, a lot of data. In which sense? They have a lot of potential predictive variables. They have a lot of features in supervised learning parlance. Okay, so we have a lot of horizontality of the problem. We had, for example, a lot of Google data. This is public data, by the way. So you can, there's an API where you can ask questions like, how many restaurants are within 200 feet, 500 feet, 1,000 feet? How many bars are between in the neighborhood? How many hospitals, and so on. So just from Google data, we had at least 100. Okay, we had some national census data. Also, how many people are living here? What's the income, and so on and so forth. And we have other data. By the way, this was specific to, even though they were started in San Francisco, later they were mostly developing in their country, which was Chile, so it was mostly about Santiago. And in Santiago, they have an origin-destination survey where people will say, where I'm going, I live here, I'm going to that place. Like normally in the morning, I take the bus from here to here, and so on. So we knew where people were working, because again, origin-destination, we say, this survey, they would ask you, I'm going to this place because that's where I study, or that's where I work, so we could estimate how many people study in this area, how many people work in this area, and so on. And also we have some own data, we had like overall price of how much is the rent in each neighborhood and so on. And this was just to start, because when I left this project, they were in the process of getting even more data. They were, for example, they were talking with some telecoms. They were in this process. I don't know if you're aware, but now it's very popular. Like all mobile phone providers, they can track where every person are, and of course they cannot sell that data at individual level, but they can sell that data because of privacy things. But they can sell aggregate numbers. So you can get, for example, from telecoms, they can tell you in this area at 8 a.m. there's so much people. Okay, so again, this was very useful for our models because you could tell. If you're, for example, want to open a new restaurant, you're very interested where more people are between 12 p.m. and 2 p.m. in some area, okay? So again, very beautiful data, very interesting, and so on. What was the problem wasn't the horizontality of the problem, it was more the verticality of the problem, okay? In supervised learning parlance, how many label instances we have. And the truth was we have very few. So for example, if we were estimating a model for Starbucks, we have 20 stores of Starbucks in the city, okay? And we know very well how much each one of those stores was selling, okay? We knew this store was selling 120, that one was selling 80. And for each store, we could add all of that data. We could have 100, 200, even 300 features if we want. But again, how many instances to learn from? Maybe 15, maybe 20, maybe 30 in best case. So first, I know this talk is about small data, and particularly I said very small. So what do we talk when we talk about small data, big data, and so on? Actually, there is no strict definition. This is my definition. This is very subjective, and you can, of course, you can tell me I don't agree with this. For me, big data has to be at least 1 billion. But again, in the context of machine learning, in the context of supervised learning, this is mostly the range we will see. Okay, we will never see, for example, a supervised learning problem trying to learn from less than 10 label instance, and the biggest we're going to see is in the millions. Okay. And as probably all the data scientists know, there's something I would call the comfort zone, where we all learned how to do machine learning. Okay, we all learned how to do machine learning from textbooks, from Coursera, from these repositories of data sets, which most of them are in the number of instances between 1,000 and 100,000. Okay. These were probably the first 5, 10 times we were dealing with our very first supervised learning models. We learned from there, and so if they throw us some kind of in that range, I think all of us we can handle that. Okay, if I give you a data set with 40,000 instances and 20 features, I'm sure like everybody can handle its own, and they can provide very good predictive models. Of course, the things start getting messy when I take you out of your comfort zone. Okay, if I put you with a lot of data, then we have the issues that everybody knows. We have computational problems. We also have problems in terms of which algorithms are more efficient, and so on. And if I take you to 100 and what I call small data, to 100 to 1,000, probably you can still keep doing what you learned to do in the other data sets, and it will still give you somehow some results, and you will start complaining that maybe these results are not very stable and so on, that you have variance problems, but you can still manage to deploy a model with 400 instances, for example. But when it gets really, really problematic is when I take you to this zone, when you have less than 100 instances to learn from, okay? And this is basically what will be the focus of my talk. Basically, by the way, small disclaimer, I will be talking mostly about problems with structured data where we had classical instance and some features. And so we are not talking about, for example, image. We're not talking about NLP. We're not talking about speech recognition. So, because I know maybe you guys, people in computer vision will have some different takes on some specific problems, but that's because it's a different type of setup. It's a different problem, okay? Again, why do we care about predicting with small data in the era of big data? The truth is, yeah, every time we will get more and more data, but actually labeled data is still, even to this date, and I'm sure it will always be like this, it will always come at a very costly, it will always be very costly. There will never be a time where we will have, I don't know, labeled data will be free. There will always be a cost involved in that. And also another reason why we care about how to predict small data is somehow come back to the basics and really learn what we are doing. And actually a lot of lessons we can learn from what works and what doesn't work with small data can help us understand what works and what doesn't work with big data also, okay? Okay, what's the minimum amount of data needed for supervised learning, okay? Before I said something like at least 10. Like I gave you a range. I said less than 10 is impossible. But with that, I didn't try to imply that actually 10 is the minimum number. And by the way, myself, before I was very skeptical about doing any type of prediction, any type of supervised learning with less than 100 instances. I remember before I used to work in a lot of predictive modeling, and I remember I was very spoiled. I was working in this consultancy firm where they were, we received many projects, and most of the time I was like, you know what, if you have less than 300 instances, it's not worth to make a model. So sorry, let's do something different in that case, but you need at least in the hundreds. Okay, so I was very skeptical that you could do any type of prediction with less than 300, 200 instances. But then I got to this project where basically I had to solve this problem. They told me, you know, this is what we do. We predict, we recommend restaurants, bars where they open, and the number of instances is this. It's at most 30, 40. We have no more, so I really have no option. Well, I could quit, but I didn't want to quit. So, so I had to take the challenge. I had to say, okay, let's try to do this. Let's try to predict with 20, 30 instances. What reference do we have related to, like, in academia, in papers, like is there any really like estimate that they say from this point you can predict and from this point you cannot predict? To be honest, there's no such thing. The closest I found is there's some papers that they say, for example, to get reasonable precision on the validation test, you must have at least 75 and 100 instances. But this is very theoretical paper. And again, what they're talking about is reasonable precision in the validation test. Okay, so it doesn't mean you cannot make predictions. It's more about inference. When you're trying to compare two models and say, is this model really better than this other model? Or you're trying to estimate out of sample accuracy. You're saying, to be really secure that's going to be this amount of prediction, you must have at least this amount. It doesn't mean you cannot make predictions with less. Okay, so again, it's very theoretical result. And there's the role of 10 by Haldar. This is actually a blog post, very interesting. And he comes with a very rule of thumb, which says like you must have at least 10 times the number of parameters in the model. Okay. Again, this is independently of the number of features. Features also has an impact, but it's like a very like rule of thumb. Okay. So I don't know if you're making, for example, a regression with just one parameter. So you have 2 parameters there. You must have at least 20 instances. For example, if you just want to do a simple linear regression with just one predictive variable. Okay. Okay. So I will be talking mainly about these 3 challenges that I faced with this when I was trying to solve this problem. First, finding suitable supervised learning algorithms that work well with small data, because not all supervised learning algorithms work well with small data. Actually, most of them they fail. So it's very interesting to share with you which are these very few algorithms that they seem to work better with small data, and that actually they don't work very good with big data. It's funny, but you will see why. Also, how do we estimate a model's error? This seems like a very technical problem. but I will show you why it's very important. Actually, this is the key issue, because when you're with working with such small data, all your estimates about how good this model, how bad this model is, it's very it's a lot of error, because it's like you're trusting a model fit in a very small data. So you really want to get this number as accurate as possible. So basically, how do you do cross-validation? And it's not so trivial how to do cross-validation in small data. And the third problem is also how to do feature selection. How do you select features, again, when you have such small data without overfitting? OK, so in terms of supervised learning algorithms, literature says models who put more emphasis on reducing variance than bias perform better in small data sets. And the opposite is true also. If you have a big data set, you should be putting more focus on managing bias rather than variance. Okay? So by the way, what is this bias and variance for the ones who don't know? We can decompose the error of a model in the bias, the variance, and what's called the irreducible error. Okay, that's the noise that always comes from the data and that you cannot do anything about it. And why it's called trade-off? Because when you put more emphasis on reducing one, for example, bias, you will have to sacrifice some variance, and the other one is true. So you cannot get both. You always have to put more emphasis either on reducing bias or variance. Actually, this is a very good way of showing what's bias and what's variance. So bias basically is how far you are from the real value on average. Okay. So for example, these two cases are the top two cases. They both have very low bias, because they're on average they're close to the. If you take the average of both will be just in the center where you want to be, right? And in the bottom cases, it does has a very high bias, because the average of them, they are very far from the center. And the variance is related to how spread your predictions are. So you want to be in a case where you have low bias and low variance, and this is the worst case, right? With high bias and high variance, where you are like completely off the target, and besides, all your predictions are like very, very dispersed. And again, this is like from the same paper. They show, for example, as you increase the training set, the variance decreases. Okay, the more data you have, the less variance you have in your model. For bias, it's the same pattern. You start reducing the bias, but it's less dramatic, the change. Okay, and that has an implication that when you take the bias as a percentage of the complete, as a percentage of how much explains of the total error, you see that as we get more and more data, the bias becomes a more important part in proportion to the variance. Okay, and what implies that for small data sets, or if you are too much on the left, that as the data set decreases, the bias becomes a less significant part of the error, or what is the same, the variance becomes more of a problem. So when we're predicting with very small data, we really, really, really need to put focus on managing variance, not so much bias. We can sacrifice some bias if we can reduce the variance. Okay, so how we can achieve more variance management? This is probably something that a lot of people have found by practice. They have found that complex models, they tend to have very low bias but a lot of variance. Okay, so if we want to reduce the variance, we need to choose less complex models. Okay, what do I say about complex models? Models with too many parameters, or which are too hard to learn, like support vector machines, neural networks. Those are very complex models. Which are more non-complex models, more simple models? You have naive Bayes, you have nearest neighbors. These are very non-complex models. Actually, this is another result also this is just one paper, but a lot of papers documenting the same, that non-complex models perform better on small data sets. Okay? And we found it's actually the same. In our case, we found that nearest neighbors, on average, was always giving us very good results. It wasn't always the top-performing model, but it was very stable, and in many different situations, was always giving us the best solution. Okay, so we were not going for a very fancy neural network or a very fancy regression. Regressions were also good, but on average, nearest neighbors were giving us always very good results. Another way to achieve better variance management, which is the same, adding some bias in order to decrease a little bit the variance, is, as you know, regularization. So also we found that regressions with penalization like Rich, Lasso, or Elastic Net were also giving us better results than just like normal regression. Okay, so in terms of learning algorithms, we found that we should prefer simple models. Now the problem is like how we actually we do accuracy estimation. Why do we want to know what's the error of a model? We could have two uses. One is to predict how good it will perform in new data, and the other one is to do model selection. Which model is better? In our case, we're more interested in doing model selection. Okay, and in the case of model selection, we're also more interested in managing variance than bias. Why is that? Basically because we don't care so much what's going to be the real error of two models, but rather when they compare their confidence intervals of their predictions, we want to really make sure that the error of this one is lower than this one. We don't care what's the real error of each one, but we just want to know sure that this interval confidence is lower than this one, so this is the best model. So we are much more interested that the variance is as low as possible, and we're not so much interested about the bias. Okay, so there are many accuracy estimation methods. Probably the most famous one is the holdout test. You just split the data in training and test. So for example, normal split will be 70% training, 30% test. You just do it once, and you predict you fit the model in the training set, and then you get the error on the holdout test. And there are some resampling methods, like the most famous one is k-fold cross-validation, and the most famous one actually is when k is equal to 10. And you have also repeated cross-validation, which is taking the average of many cross-validations. You also have leave group out cross-validation, and you also have the bootstrap. I will be just talking this time about cross-validation because the other ones, even though bootstrap can be competitive with k-fold, actually Monte Carlo cross-validation is not, in general, it's not that good. Okay, holdout test. This is the most famous one. This one actually you should try to avoid it, and there are only there's only one specific case where you should use holdout test. Only if data is very large, okay, and if only you're interested in the model's performance. If you're not interested in doing model selection, if you're doing model selection, even if you have big data, it's always better to do cross-validation. Again, for the same reason that of variance. About k-fold cross-validation, what k? So, for example, here we see the bias. Of course, the bigger the k, you will be more close to the real predictive error. So you will have lower bias. But also, the bigger the k, you also will have a bigger variance. Okay, so for a small k equals more bias but less variance. And for a large k, being the extreme case of leave one out cross-validation, you have less bias but more variance. Okay? Since we're doing model selection and we're working with small data case, we should prefer a small k. A small k means basically a k of 2, 5, or 10. 10 at the most. But we should really avoid the case, for example, of leave one out cross-validation. And there are two results there. First, this is a very well-known case that leave one out has very high variability, and also that for model selection you should always prefer tenfold cross-validation over leave one out. Okay, this is very technical note. I will skip. Repeated cross-validation, yes. you should do it. It's very recommended. So normally people do tenfold cross-validation and they stop there. Actually, it's a very good practice to run your tenfold cross-validation at least 5 times, okay? And take the average of all of those ones. Why? Because it has no effect on bias, so it's not going to worsen your bias, but you are going to gain reducing some variance. And in particular, the effect is much more bigger when the k-fold is 2 or 5. So the smaller the k, the impact of doing repeated cross-validation will be better. Okay. For 10, you also will get some gains. And again, if you have in the extreme here, like leave one out, you will have almost no effect doing repeated cross-validation. The impact will be mostly if you are doing cross-validation with a small k. And by the way, repeated cross-validation, normally there's also a result there that it's not that useful when you have big data. When you have more than 200 instances, actually you don't gain too much variance reduction from repeating cross-validation. So this applies mostly for small data cases. Another question, is model selection equals model-based accuracy? In particular, for the case of small data sets, I would say no, because there's so much noise in your model that you really want to make a double check. So we have there many models, but I would say no. Normally, you always want to make a double check of your model, that your model also makes some sense. You want to do this domain expertise, that somebody checks that the variables in your model make sense, that the predictions make sense. But this is particularly true for the case of small data. Here's an estimation that we did from our model. This is the plot of the Santiago, of the city where we're making the model. And then here are the predictions. How much is going to sell each store? I don't remember if this one was a pizza place or was a coffee shop, but again, it doesn't matter. Basically, what we saw there and what we were very happy with this model is because it represented very well the main streets of the city. So we didn't tell the model, here's a big street, here's something. We just were throwing variables, and the model was able to, when we plotted over a map, the predictions made sense. And by the way, not all the models, the predictions were making sense. So even though we could have like top 10 models, and we could have all of them with more or less normal accuracy, maybe for 5 of them, they were making predictions that will make sense, like from a, not business point of view, but more like they will make like general sense. And the other ones were making predictions like, I don't know, oh, the coffee, you should open a coffee there where there's like residential place, and we knew that that was not true. So the main take from this is like, just also always incorporate some domain expertise on your decision when you pick a model. On feature selection, we'll go very fast. When the data is very small, I will really face a problem of overfitting on the feature subset space. Which is the same that if you try too hard to learn to do these very data-driven approaches of feature selection, like any of these where you try wrappers or so on, you will find some features, especially if your feature space is very big, you will find some features that are very correlated to what you're trying to predict, but that doesn't mean that they will predict very well in new data. Okay, so you will be overfitting. Even you will be overfitting not only in the training set, but actually you can even overfitting on your validation test, because you have so much small data. For example, again, you have 20 cases. Even if you do cross-validation, maybe all the 10 combinations you will do, you will still think that the model with those features predict very well, but I give you new data and it will predict awful. Okay. So the risk of overfitting will always be bigger the bigger your feature space is, like if you have 500, 1,000 features, and you will always find something that correlates very well. For example, this is a very interesting case where, also from the same paper, these guys, they created some artificial data set, non-informative features. So imagine you created 100 features. All of them were generated completely random compared to what you were trying to predict. And again, you have very small case, like maybe 20, 30 instance. And then you run some, for example, forward selection. And you ask this, oh, okay, how good is the predictive model you found? All they found, the more you try, for example, the one that's more optimistic is the top one, which only has 100 instances. And they said, oh, we found a model with these features that predicts 80%. It's not true, because the real model should predict 50%. It's completely random, okay? But again, you tried so hard that in your validation test, you found a subset of features that, according to your own cross-validation, said it predicts 80%. It's not true. Of course, as you have more data. For example, the tick line is 500 instances. This was fooled less. He didn't expect he was actually finding a model that predicted 80%. They said, oh, we found a model that predicted 60%. But still was fooled, because there's no model who should predict more than 50, which is a flip coin. A final point is how to use complementary data. Can we use unlabeled data to help the model learn? So suppose, again, you are in the case of Starbucks, and you have maybe 40 Starbucks in the city, but you only know the sales of 20. Can you use the data of the other 20 Starbucks you don't know? And the answer is yes, and there's a technique called semi-supervised learning to do that. How it works, this is just one way of doing semi-supervised learning. It's called pseudo-labeling. Basically, you have the labeled data, so you have the 20 Starbucks, you do know the sales. You train a model for that. And now you use that model to predict the sales of the other 20 Starbucks you don't know data, okay? So you predict the unlabeled data. Now you have 40 Starbucks, 20 of them with the real sales, and other 20 Starbucks with the prediction you made, okay? Now you do, okay, now I'm gonna fit a model over the 40 Starbucks, assuming the 20 that I predict are real sales, okay? And then you have an overall model. That's how you can use unlabeled data to fit your model also. Why it works? Suppose the case we have there on the left, we are just fitting a model with those 10 instances we have, okay? We have 5 positive, 5 negative. We only have only those cases. You will assume that the boundaries will look like that, right? On the left, an ellipsis. On the right, that centroid. Let's assume we put like thousands of unlabeled data. Those are those green points. Then the model will understand that actually the data generation is more like, not like an ellipsis like in the left, but more like also a centroid on the left. Okay, so it will have like a better sense of which are the boundaries of your model. Did it work for our case? I would say 50-50. For one coffee shop chain, we did the model where it had 24 label instance. That's the coffee shop we were working with. And then we tried with using the data of 37 other coffee shops similar to this one, but they were not our clients. We found that actually it helped. It decreased the mean average error by 6%. But for a pizza chain, we tried the same. We had the 20 label instance of that chain we were working with, and we added some non-labeled data from the competition, again, just where they were, like where these other pizzerias were, but we didn't know how much they were selling. And we saw no improvement in that case. Okay, so very quick summary. Small data prediction is basically it's a high variance problem. You are very always on the risk of overfitting. Learning algorithms, you should always prefer nearest neighbors and regression. And regression, of course, try to do some regularization. Accuracy estimation, cross-validation is a must. You cannot choose. You always have to do cross-validation with your small data. And you should prefer 2-fold or 5-fold over 10-fold. And also you should prefer repeated cross-validation. For model validation, try to not only use accuracy if you cannot, and try to add some domain expertise also. If you cannot, okay, but ideally, you want to do that. The same for feature selection. You also want to do it not just data-driven methods, but also you want to add some expertise knowledge to that. And also, semi-supervised learning can help adding unlabeled data. And just one last point. There's a very interesting blog post from LDEP He makes 10 recommendations for working with small data. I will just point 5 that which were not present in my presentation. The first one is hire a statistician, because he says like statisticians are experts in working with small data. No pun intended, but actually statisticians were the first data scientists, and they were always working with 5, 100, 200 instances before the big data came. So they are really the people who are more experts on this. Do clean up your data, because you're much more sensible to outliers or missing data. Use model averaging. I didn't mention this on my presentation, but we also tried that. We tried to average different models. So for example, we will have a regression and a nearest neighbor. So we will combine the predictions, and actually the predictions will improve. Try Bayesian modeling. Okay, so again, if you guys are familiar with Bayesian statistics, you know that this is a way you can add domain expertise to your model. You have prior knowledge. You know that, for example, in our case, in this area, it should be very high, the sales, and this one should be very low. You have some domain knowledge added to the model. And the last one prefers confidence intervals to point estimates. Again, this is actually a recommendation that, for some reason, a lot of people don't follow everywhere in machine learning. It should always, even in big data cases, I agree we should always be talking about confidence intervals more than point estimates. So rather than saying my model predicts 83%, we should say something more like we predict between 80 and 85. People never report their confidence intervals, but they're very important. But it's even more important for small data cases. Okay. So that's it.
Thank you very much. So, questions. The first hand, please.
Have you tried or considered data augmentation or transfer learning for your problem?
Okay.
Is it possible?
Yeah. So the case of transfer learning, actually, it's something I wanted to talk, but I had to reduce the talk. Transfer learning is something very used in computer vision, in neural networks, where you can actually use a pre-trained model and something. And actually, we had the same idea. We didn't call it really transfer learning. It's more like pooled data. So it's, for example, suppose we have Starbucks data in Santiago and Starbucks data in San Francisco. Okay, so these two models, in theory, they're two different models. Okay, you don't want to fit just one model because you want to keep them like this one is this one, but you would like to know maybe there's some patterns that are common worldwide, right? Like maybe people prefer more to go to coffee shops close to their work rather than where they live. Maybe there are some common patterns, or you would like to transfer that knowledge from here to here. What we do with pooled data, we never implemented, but we discussed a lot of ideas in this particular case. Is you can do something like you can add new data, but less pooled than the data you are trying to target. So for example, your target is Santiago, not San Francisco. So you can say, I'm going to oversample Santiago so it's more present, like for example, 3 times more than San Francisco. So I will start adding data, like contaminated data, that's not really from the nature, but a small one, see if there's an improvement. If there's an improvement, I will add it with more weight, and you can start like adding little by little. But the very idea of transfer learning really doesn't apply, like as neural network people do, it really doesn't apply to this case because we're not really doing this. Again, as I said, disclaimer, we're not really doing like computer vision or this type of thing. So we cannot really apply the very same concept, but we can apply like the idea of that. Okay.
Sorry, maybe a bit ignorant question, but how can you validate your data without domain expertise? So you made some prediction. How do you know how close it is to truth?
It's more than, but yeah, it's validation in the sense not of accuracy, it's in the sense of like double checking that your model makes sense. So for example, in this one, when we talk about domain expertise, we are not talking about we need to try like bring an expert in urban planning or something. For example, in our case, it means just validation in the sense that we know, like we know people that they can tell you in this place it's not correct that, for example, a restaurant could sell a lot because there's nobody living there, for example. So the more that's the domain expertise. Exactly, that's the domain expertise. Yeah.
But without domain expertise, can you validate data?
Yeah, we have accuracy methods. We have all what we talk about how we can do cross-validation and so on. The only thing I've said is like even those accuracies will have like very high confidence intervals. So you have to take with a salt of grain what those accuracies are saying. So they shouldn't be ultimate. Actually, the approach we used was like trying many models, okay, make some kind of pre-selection. Like we used, for example, the library Caret in R. So they have more than 100 supervised learning methods. And we saw that consistently there were like 10 algorithms that were always performing in different data sets better with small data. So we will come to some pre-selection of models. You know, we have 10 potential models. Then we will use the domain expertise, and we will help us select among those 10 models. Okay, so you do like 2 steps where you do some kind of discard some models because they really have very low accuracy across different data sets, and then you will pass to some more like domain expertise, which will allow you to select the final model. Also, we had, by the way, a business restriction, which was like whenever we wanted to use this model, and this is a very common problem, the client wanted that the model made sense. So the variables made sense to him. So we also had like this business restriction that we also needed to include in the model selection. We couldn't do like 100% data-driven method.
Can you share with us some methods to do feature selection, maybe reduce number of features that you used practically in that small number of data?
Number of features, actually, we tried to reduce it to no more than 5. Actually, but there was also a business definition that we had to stick to either 3 or 5 models, 3 or 5 predictive variables. We couldn't use more. That was a business definition. Again, because when you wanted to explain to the client, you couldn't explain something. But also made sense from the technical point of view because, again, if you use too much, you will overfit. If you have 20 instances and you are doing a model with 10 features, I can guarantee you're overfitting. How we did feature selection, actually, there was we used like data-driven methods, but we also used some kind of discard some features, like from business point of view, which, for example, if we were talking with a coffee shop, we knew that the coffee shop didn't want us to include variables like I don't come now, but we knew that there were some variables that were going to be very noisy for him, so we'll discard a priori. Then we will use the data-driven method. We will reduce that again to, for example, 10 features, and then from these 10 features, we'll use many different models. And then we will select which one will make like a good balance between accuracy and between that domain expertise. Yeah.
Your problems are mostly classification or regression?
This was a problem, by the way, I didn't mention, but this was a problem of regression.
Regression.
Yeah, because we're trying to predict sales. So sales, we normalized sales to some scale that like 100 was the average. So it was something where we were trying to predict something that was between 60 and 200. It was a continuous variable.
Yes, but the error you represented was accuracy.
No. So there are some. For example, all the results from our side, they are like, for example, absolute error, the quantiles, and so on. The other results we were showing, there was like some theoretical results from some papers that both classification and regression. So, for example, this one. This one talks about accuracy, but this is not our work. This is like this is a paper.
And you tried bias variance trade-off in your work, yes? And have you tried VC analysis for detecting, for estimating how much data you need?
No. We didn't do any like theoretical point of view like BC, but for example, for controlling bias variance trade-off, for example, in the case of a nearest neighbor, we know the bigger the K, the lower the variance that we want, right? You have more bias and you have lower variance. So I didn't mention this, but the nearest neighbors, we found actually was always using a K very big, like 8 or 10, which for a 20 instance is quite a lot. Like if you use K equal the number of instances, basically you have a null model. You are predicting like the average of all the instance, right? So it was always, that was the way we were playing with the bias variance trade-off was always, for example, with the parameters. We knew that, for example, in the case of nearest neighbors, the bigger the K, could reduce the variance, and we could like, that's how we balance bias and variance, bias and variance in the case of the classifiers, in the case of this regression.
Thank you.